We are continuing with part 2 of the slides. Now, in the previous slide, we just said that inputs can be substituted for one another, obtaining a particular output. So as you move along the isoquant, you can imagine a trade-off happening between labor and capital. So one more unit of labor means some amount of capital must be traded, but output remains constant. Now, this is called the slope of the isoquant. We know that because the isoquant is downward sloping, it has a negative slope. And the slope is called the marginal rate of technical substitution. And it can be defined as the amount by which the quantity of one input can be reduced when one extra unit of another input is used, so that output remains constant. Now, if we have a look at the formula over there, you can see that your marginal rate of technical substitution, we know that it's downward sloping, hence the negative slope, but it's given by the change in the capital input, which is the variable on your y-axis, over the change in the labor input, which is the variable on your x-axis or horizontal axis. And now we can just use the symbols delta K to represent change in capital over delta L to represent the change in labor. And this is for a fixed level of output. So Q represents output. So in the same way that we said our marginal rate of substitution for the indifference curve was diminishing, we here can also show that your marginal rate of technical substitution is also diminishing. So your marginal rate of technical substitution falls because it becomes less negative as you're moving down the isoquant. And we have seen that this curve has a convex shape. So let's just discuss this aspect of diminishing marginal rate of technical substitution. Notice that the slopes versus the slope of your indifference curve versus that of your isoquant. For the one, we speak about the MRS. Here we speak about the MRTS. Okay, so as you move along your isoquant, as you use more labor, there's this increased use of labor. So a positive change in labor, that means there's going to be some additional output. So that MPL stands for your marginal product of labor. That is the additional output you are going to get for that extra units of labor that is being used. But similarly, as you move down that isoquant, you're having a situation where there is a reduction in how much capital is being used. So there is a decrease in the use of capital. So there's a change in K and it's a decrease in K because, of course, we are using labor now instead of capital. So that is the change in capital. But because of that change in capital, the marginal product of capital, there is a reduction in output as a result of that decrease in the use of capital. So that MP with the subscript K stands for your marginal product of capital, and there will be a reduction in output from the decreased use in capital. But we know the net effect on output Q all along your isoquant is in fact the same. So the net change, even though you're having the product of your change in labor times your marginal product of labor, the product of that is positive and increasing. There's an increase in that additional output. And here you have a reduction in output because you're using less capital. So the product of your marginal product of capital times the change in the capital, we know that there's a reduction there. The net effect of that is that in terms of output doesn't change. So the change in output must be zero. Hence, we on your right hand side, we have zero because we're keeping output constant. Moving along that isoquant, the total change must be zero. So now by rearranging the terms, if we take this term over to the other side, it will of course become negative, and then we can rearrange such that we have our ratio of our marginal products equal to the negative of your change in capital over your change in labor. And this gives you your slope. We just saw that your marginal rate of technical substitution is your change, the negative change in your capital over the change in labor. We just saw that that is our slope. And here we have shown that our ratios of our marginal products is equal to our slope, which is equal to our marginal rate of technical substitution. So please, this equation 6.2, this is very important, right? So your marginal rate of technical substitution can be given by the ratio of your marginal product of labor, that is your variable that is on your x-axis, over your marginal product of capital, the variable that is on your y-axis or your vertical axis. Figure 6.6 demonstrates the marginal rate of technical substitution. Now you can see that we've got our vertical axis labeled as capital per month, and our horizontal axis is still labor per month. And we have three isoquants, each with different output. Q1 has an output of 55, Q2 has an output of 75, and Q3 has an output of 90. And you can see as these isoquants move further away from the origin, the output for each isoquant is more. And similar to your indifference curves, you can see your isoquant is downward sloping and it is convex in shape or bowed inward. So the slope of your isoquant, it measures the marginal rate of technical substitution, and that is the ability of the firm to replace capital with labor while keeping the same level of output. So we're going to look at one particular isoquant, and that is Q2. So initially, you can see that as labor increases from 1 unit to 2 units of labor, we can see our change in capital over our change in labor gives us a marginal rate of technical substitution equal to 2, right? But then as we move from 2 units of labor to 3 units of labor, our marginal rate of technical substitution becomes, there's your change in K over your change in L, it now becomes 1. And as you move from 3 units of labor to 4 units of labor, you can see the change in K now is 2 over 3 over 1. So now your marginal rate of technical substitution is 2 over 3. And lastly, it becomes, between these 2 points, it becomes a third. So you can clearly see that as we are adding more labor and replacing the capital with more labor, labor is essentially becoming less productive. That's important to note, and capital is becoming relatively more productive. And that is also illustrated by the fact that the curve becomes flatter as you move along the isoquant towards the horizontal or your x-axis. And all this occurs on Q2, which had an output of 75 units. The same rationale can be applied to Q1 and Q3 respectively. Now there are two special cases of production functions, and these are two extremes of production functions, namely your perfect substitutes, and the other is where you have fixed proportions production function. Now, this represents the possible range of input substitution in this production process. So the first one that we can look at, we'll see in the next slide, is for perfect substitutes. But for now, let's just define what fixed proportions would be. So that is where you have a production function that has an L shape. So your isoquants are L shaped so that you find that only one combination of labor and capital can be used to produce each level of output. So you find that there needs to be these fixed proportions in terms of the combination of labor and capital for each level of output. So if you want to increase output, that fixed proportion of L and K must occur. So with your fixed proportions production function, that describes a situation where your method of production tends to be limited. Now, this first case or this first example we're going to look at is when inputs are perfect substitutes. Now, we understand what substitutes implies. So what does perfect substitutes imply? So here you can see that your marginal rate of technical substitution is the same for all points on this curve for A, B, and C. So your MRTS is the same for all points. Remember, your MRTS is your slope. And you can see that you've got a straight line. Your isoquant is a straight line, so that implies that your slope is constant. So your MRTS is constant. So for points A, B, and C, on this isoquant Q3, your MRTS is going to be constant. So at point A, you have a situation where a lot of capital is being used and less units of labor. And at point C, more labor input is being used and less capital. And B is a combination of the both, but all three of these points on Q3 achieve the same level of output, no matter what the level of input being used. So A, B, and C represents three different capital labor combinations that generates Q3. Now, if we have a look at 6.8, this is where we have fixed proportions production functions, and these production functions are L-shaped, right? And you have this line drawn from the origin through the points A, B, and C. For each output, Q1, Q2, and Q3, there is a specific combination of labor and capital. So if we look at point A, the combination used of your inputs, labor, and capital is L1 and K1. So if we want to move to a higher isoquant, Q2 or Q3 respectively, for that higher output, it can only occur if labor and capital are both added in fixed proportions. So only one combination of labor and capital can be used to produce a given output on isoquant Q1, on isoquant Q2, and isoquant Q3 at those points A, B, and C. So adding more labor alone isn't going to increase output, nor does adding more capital alone does. It must be increased with the same combination or proportion of labor and capital in order to increase output. Now here we have an example, 6.4. Again, please go through it for knowledge enrichment purposes, and it is about the production of wheat. So please read through the example, and it presents a nice practical example to work through. But very briefly, you can see that with wheat farming, production technologies can either be capital intensive or it can be labor intensive. So the marginal rate of technical substitution would be relatively high if it was a high capital to labor ratio, or your marginal rate of technical substitution would be lower if it had a lower capital to labor ratio. And that exact ratio or combination of those inputs is going to depend on the input prices, and that is where chapter 7 comes in, looking at the cost constraint. So here you have the figure for 6.4 being plotted, and you can see that you have your isoquant, and the output is given by 13,800 bushels per year. And it can, of course, be produced with different combinations of labor and capital. So at A, you have a more capital-intensive production process, whereas at B, you have a more labor-intensive production process, and the MRTS, which is your slope, can be determined by your change in K over your change in R, and that gives you an MRTS between A and B of 0.04. So just read through the example. I'm concluding part 2, and I will continue with your returns to scale.